in this example, we're going to consider what's called an elastic head-on collision. And before I give you the specific example I have in mind, let's talk about it generally. So let's suppose I have mass m1 and mass m2, and m1 has some velocity v1, and m2 has some velocity v2. I want to know something about the situation after they hit each other. Now, we're not going to do anything crazy where their masses are changing along the way, at least not yet. But some questions I might want to know are, what are v1, what's v2, and let's be clear, starting. And then I'm going to ask you, after they collide, what's v1 final, what's v2 final. Now, I obviously have to give you some other piece of information, and I'll tell you that if you know any two of these things, you can find out the other two. The way you do that is by you taking the conservation of momentum, and that's just that the sum of momentum at the beginning equals the sum of momentum at the end. And I use, let's call this maybe J or something. So I means initial, beginning, F means final. This will always work for any type of collision. Momentum is always conserved. In fact, you could just, how embarrassing. Momentum is always conserved. And that seems to be one of the most fundamental things of the universe. In fact, if you just imagine the universe as a big box, you could imagine some external thing out here shouting at the universe, momentum is conserved, making it true. In fact, there are some that think this is the deep connection in the universe, momentum is conserved, and that somehow we get Newton's third law. Well, not somehow, but we get Newton's third law out of this. But the deeper thing is that momentum is conserved. So I'm saying that a lot because this will solve so many problems in Physics 113, especially in this unit. Momentum is always conserved. Just kind of keep that in your head. So we can use that, and then let's say we have two objects. I'm just going to do the case of two objects. If I write out what momentum is, so momentum is mass times velocity. And it gets messy, but it's worth remembering. m1, v1 initial plus m2, v2 initial equals m1, v1 final plus m2, v2 final. So keep in your head, and I know it seems crazy now, but if you just walk around for a couple days and every time you see someone bump into someone else, just say this, because they're obeying this equation when they bump into each other. m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f, and so many problems can be solved with this equation. I'm also going to use the fact that the sum of the kinetic energies, and this one that I'm about to tell you is just for an elastic collision. So sum of kinetic energies at the beginning will equal our sum of kinetic energies at the end. So this is always, and this is elastic. Elastic just means we're conserving our sum of potential and kinetic energy. And in particular, it means elastic means we're conserving our sum of kinetic energy. I'm getting ahead of myself to a different kind of problem. Okay, so we are conserving the sum of kinetic energies. That's what an elastic collision means. And in this case, we're doing an elastic head-on collision. The head-on part meaning that we only have to consider one dimension. They're not going to bounce off in another dimension. So this is all in x. They're not going to bounce off in y. And from here, I can say 1/2 m1 v(I) squared plus 1/2 m2 v(2I) squared 1/2 m1 v1f squared plus 1/2 m2 v2f squared. And then you can solve for whatever you want. So to make this problem not take hours on end as I just slog through algebra, I'm going to go ahead and write down, if you take these two equations and work them out, what our relationships are between final and initial conditions. So if you work all this out, you'll find that v2f equals twice mass 1 over m1 plus m2 times v1 initial minus m1 minus m2 over m1 plus m2 v2 initial and v1f equals m1 minus m2 v1 initial over m1 plus m2 2 m2 over m1 plus m2 v2 initial. And in the special case we're going to solve, we're going to have v2 initial be 0. So in that case, both of these terms go away. So if v2i equals 0, this simplifies to v2f equals 2m1 over m1 plus m2 v1 initial and v1f m1 minus m2 over m1 plus m2 v1 initial. That's a lot. It is not necessary that you memorize these. I just wrote them down instead of going through all of that so that this problem doesn't take a crazy amount of time. What you should do is see if you can get these out, or in the specific example I'm about to do, try just plugging in numbers. And in fact, often with these two equations, plugging in numbers before you manipulate variables is the easiest and clearest way to go. So you might have crazy numbers in here, like 3 times 10 to the negative 27th. And you'll find that often the person who wrote the problem didn't want to deal with crazy numbers either. And so what they did is they put it so that if you started dividing out the masses, you'd notice that like the ratio of masses is 2. And so just try to simplify every step with the numbers when solving collision equations would also be my pro tip. So now that we have this, we can do any situation we want. So here's a specific example that's close to something you might see on WebAssign. Suppose I have a neutron traveling at 3 times 10 to the 5th meters per second. And let's have that one be v1i, 3 times 10 to the 5th meters per second. That is 10 to the 5th. And it has a mass of 1.67 times 10 to the negative 27th kilograms. And it's going to collide with a deuteron with mass 3.34 times 10 to the negative 27th kilograms. Right? Well, now it's just plugging in numbers. And if I plug the numbers in, you'll find that the velocity of my neutron at the end is 1 times 10 to the 5th meters per second. And the velocity of my deuteron at the end is 2 times 10 to the 5th meters per second.